Buckle up for the ultimate voyage across time, stars, and cosmic dust. This is not just a journey through space. It's a journey through the heart of the Milky Way galaxy, where mysteries await at every light year. In ancient times, a great many civilizations held the belief that our planet Earth was the very center of the entire universe. This long-standing and deeply rooted perspective was extensively supported by notable philosophers and thinkers of the time, most prominently Aristotle and Ptolemy. Their teachings formed the basis of what came to be known as the geocentric model. Within this conceptual framework, it was assumed and widely accepted that all celestial bodies, including the sun, the moon, the stars, and the wandering planets, traced circular paths around the Earth. These circular orbits were seen as perfect and harmonious, a reflection of the divine order believed to govern the cosmos. The model was embraced by the wider populace for centuries and heavily endorsed by powerful institutions, particularly the Church, because it reinforced theological notions that placed humanity, and by extension Earth, at the center of creation. Observations of the sky with the naked eye seemed to support this model. The sun appeared to rise in the east and set in the west. The stars moved in predictable patterns, and all visible celestial motions could be interpreted within the framework of Earth being stationary and central. However, a monumental shift occurred during the 16th century when a Polish astronomer named Nicholas Copernicus introduced a bold and revolutionary concept that would ultimately transform our understanding of the universe forever. Copernicus proposed what came to be known as the heliocentric model. In this model, the sun, not the Earth, was posited to occupy the central position in the universe. According to Copernicus, the Earth, along with the other known planets, revolved around the sun. This radical departure from established belief challenged the prevailing wisdom and directly confronted both religious dogma and centuries of scholarly consensus. Though the Copernican model still maintained the idea of circular planetary orbits and retained some inaccuracies inherited from earlier theories, it marked a crucial turning point in astronomical thought and paved the way for a scientific revolution. In the generations that followed, the heliocentric model underwent refinement and gained robust support from observational evidence and mathematical advancements. Johannes Kepler, a German astronomer and mathematician, improved upon Copernicus's ideas by demonstrating that planetary orbits were not perfect circles, but rather ellipses. This crucial insight, derived from meticulous analysis of data gathered by the Danish astronomer Tycho Brahe, brought the heliocentric model into closer alignment with observed celestial behavior. Soon after, Galileo Galilei made groundbreaking contributions by applying the newly invented telescope to astronomical observation. With this instrument, Galileo made several key discoveries. He observed 4 moons orbiting Jupiter, revealing that not all celestial bodies revolved around the Earth, and he documented the phases of Venus, which could only be explained by a heliocentric system. These observations delivered powerful blows to the credibility of the geocentric model. Despite the revolutionary nature of Galileo's findings, his advocacy for the heliocentric model met fierce resistance, particularly from the Catholic Church. Galileo was tried by the Inquisition and forced to recant his views, spending the remainder of his life under house arrest. Nonetheless, his work had already planted seeds of transformation that could not be uprooted. The acceptance of the heliocentric model marked a profound and irreversible change in humanity's understanding of its place in the cosmos. It symbolized the triumph of empirical observation and reason over dogma, and opened the door to modern science, encouraging generations to question established authorities and seek truth through evidence and experimentation. Having grasped the revolutionary nature of the heliocentric model and its implications, we can now explore the magnificent story of how our solar system itself came into existence. According to current scientific understanding, the solar system formed approximately 4.6 billion years ago from an enormous and diffuse cloud of gas and dust, often referred to as the solar nebula. Over time, due to gravitational forces acting within the cloud, this nebula began to collapse inward. As it collapsed, it started to spin faster and gradually flattened into a rotating disk. At the center of this disk, gravitational compression generated extreme pressure and temperatures, eventually igniting nuclear fusion and giving birth to our sun. The remaining material in the disk did not vanish. Instead, it coalesced and began to clump together through a process called accretion. Microscopic dust particles and frozen grains collided and fused, forming larger bodies called planetesimals. These planetesimals continued to collide and merge, growing in size to become protoplanets. Over millions of years, through countless interactions and chaotic collisions, these protoplanets either became fully fledged planets or were destroyed in the violent crucible of early solar system dynamics. The structure of the developing solar system depended heavily on the distance from the newly formed sunday. In the inner region of the solar disk, temperatures were too high for volatile compounds like water and methane to condense. Only materials with high melting points, such as metals and silicates, could solidify and accrete. This is why the 4 planets closest to the Sun, Mercury, Venus, Earth, and Mars, are terrestrial, rocky planets with relatively small masses and thin atmospheres. Farther from the Sun, in the colder regions of the solar nebula, conditions were favorable for ices and gases to accumulate. In this region, massive protoplanets formed by gathering vast envelopes of hydrogen, helium, and other volatiles. Jupiter and Saturn, the gas giants, emerged with immense sizes and deep atmospheres rich in these primordial elements. Jupiter, in particular, exerted a dominant gravitational influence over the solar system, shaping the orbits of countless smaller bodies and possibly preventing the formation of another planet in the region that became the asteroid belt. Saturn followed as another gas giant with its own complex system of rings and moons. Beyond Saturn lie the ice giants Uranus and Neptune. Though smaller than Jupiter and Saturn, these planets are nonetheless enormous and consist largely of icy materials and gases. Their formation and migration played significant roles in scattering planetesimals and shaping the architecture of the outer solar system. Extending beyond Neptune is a distant, icy region known as the Kuiper Belt. This zone contains countless small bodies composed mostly of frozen volatiles, as well as dwarf planets like Pluto, Haumea, and Makemake. Even farther still, stretching to the outermost edges of the Sun's gravitational influence, lies the hypothesized Oort cloud. This spherical shell of icy debris is thought to be the source of long-period comets that occasionally make their way toward the inner solar system, illuminating the skies with spectacular tails as they pass near the Sun. The formation of the solar system was not a unique event. It followed universal principles governed by gravity, thermodynamics, and chemistry. As we study planetary systems around distant stars, known as exoplanets, we find that many of them share features with our own solar system, from rocky inner worlds to gas giants orbiting farther out. These observations support the theory that the processes that shaped our solar system are common throughout the galaxy and possibly the universe. In conclusion, the transformation from ancient geocentric worldviews to a heliocentric understanding of our solar system, and our growing comprehension of how the solar system itself formed from a cloud of cosmic dust, reflect the incredible journey of human knowledge. This intellectual evolution stands as a testament to our species' relentless curiosity, our willingness to question the unknown, and our capacity to uncover the workings of the universe through observation, reasoning, and scientific endeavor. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.